So in solving equilibrium problems, we have 7 basic steps to follow. So first, you need to write the balanced equation for the reaction if the problem doesn't give it to you. And then from there, you can write the equilibrium expression. Next, you want to list your initial concentrations, and with those you can determine which way the system will shift to achieve equilibrium. Sometimes this is easy, for example, if you have all reactants but no products, while other times you may need to calculate the reaction quotient to find out. Then you want to define the change that the reactants and products will undergo to reach equilibrium, and since this is often unknown, you want to use a variable x. And then with that change, you can define the equilibrium concentrations of each species in terms of x by applying this change to the initial concentrations. And then you want to plug in those equilibrium concentration expressions into the equilibrium expression, and then from there you can solve for x, and then once you have x, you can figure out the final concentrations of all these species. So let's look at an example. Say we have 3 moles of hydrogen and fluorine gas added to a 1.5 liter flask where they react to form gaseous hydrogen fluoride, and the equilibrium constant for this reaction at this temperature is 1.15 times 10 to the second. So we want to find the equilibrium concentrations of each species. So the first thing we do is write the balanced equation. We have H2 plus F2 producing 2HF. And then step 2, we can write the equilibrium expression. K, which is equal to 115, is equal to the concentration of HF squared because of the coefficient, divided by the concentration of H2 times the concentration of F2. And then initial concentrations for H2 and F2, we have 3 moles in 1.5 liters, so the concentrations are 2 molarity. And then we have no HF initially. So since we only have reactants, we already know that the system will shift to the right to reach equilibrium. So we don't have to calculate the reaction quotient in this case. And then next we need to define the change needed to reach equilibrium. So looking at this balanced equation, we can determine from the coefficients that since H2 and F2 are in a 1-to-1 molar ratio, then if H2 decreases by x, we know that these will decrease because the reaction is going to shift to the right. So if the concentration of H2 decreases by an amount x, then F2, since it has the same coefficient as H2, the concentration of F2 will also decrease by x. And then hydrogen fluoride has a coefficient of 2, so it will change double the amount that these change because of its coefficient. So if the concentration of these two decreases by x, then the concentration of hydrogen fluoride will increase by 2x because it's being produced while these are being consumed. So we can represent this with the table, which is often called an ice chart. So here we have the balanced reaction, and then underneath each species we write the initial concentration, the change, and then the equilibrium concentration. So H2 and F2 both start with 2 molar, and then they will decrease by some amount x. And we don't know what x is yet, so we just leave it here. So the equilibrium concentrations will then be 2 minus x. while for hydrogen fluoride, we start with 0, and then this concentration will increase by 2x, because again, whatever H2 and F2 change by, HF will change by double that amount, since it has a coefficient double that of these coefficients. So the equilibrium concentration of hydrogen fluoride will be 2x. So then we can plug these into the equilibrium expression. So we just plug in 2x for the concentration of hydrogen fluoride and 2 minus x for the concentrations of H2 and F2. And so this simplifies nicely into 2x squared over 2 minus x squared. So when it simplifies like this, we can just take the square root of both sides. So we get that the square root of the equilibrium constant, or the square root of 115, is equal to 2x over 2 minus x. And from here, all we have to do is solve for x. And if you do that, you find that x is equal to 1.69. So that means the concentrations of H2 and F2 decreased by 1.69 in order to achieve equilibrium. So the equilibrium concentrations of H2 and F2 are 2 minus 1.69, or 0.31 molar, while hydrogen fluoride increased by 2x in order to reach equilibrium. So the equilibrium concentration of hydrogen fluoride is 3.38 molar. And so, since this K is pretty large, before we even solve the problem, we can predict that the equilibrium concentrations will be very product favored since it's so large. And so notice how these results support that prediction. The concentrations of the products at equilibrium is much greater than the concentrations of the reactants. So in a lot of problems, the equilibrium constant will be very small. Now remember that this means that the reaction does not occur to any significant extent. And so that means x will be a very small number. So we can often ignore the plus x or minus x terms to simplify any calculations. Because in the last problem, it simplified so that we could just take the square root of both sides. But in more complicated problems, you'll often have to solve a quadratic equation. So, but we can use this to simplify it so we no longer have to solve that quadratic equation. So if we have 1 mole of NaOCl in a 2-liter flask, and then it decomposes into NO and Cl2, and the equilibrium constant for this reaction is 1.6 times 10 to the negative 5th, which is a very small number. So here we write the balanced equation first, and then the equilibrium expression. And initial concentrations, we have 0.5 molar of NaOCl, and then we have no products yet. So NaOCl and NO both have a coefficient of 2. So whatever the concentration of NaOCl decreases by, the concentration of NO will increase by the same amount, since the coefficients are the same. And we know that the system will shift to the right, producing more products while consuming reactants, because in the initial state we have only reactants and no products. And so Cl2 has a coefficient of 1, which is half the coefficient of these two. So whatever the concentration of NO increases by, the concentration of Cl2 will increase by half that amount. So now we can set up an ice chart. So for NaOCl, we initially have 0.5 molar, and then we say the change to reach equilibrium will be minus 2x. So the equilibrium concentration is 0.5 minus 2x. While NO and Cl2 both start with 0 molar, but they increase by different amounts because of their different coefficients. So NO will increase by 2x, the same as NaCl decreases by, and then Cl2 will increase by x. So their equilibrium concentrations are 2x and x. And then we can plug these equilibrium concentrations into the equilibrium expression. So we get this. Now, usually we'd have to expand this expression and solve a quadratic equation. But since K is very small, the reaction does not proceed much, which means that while the concentration of NaCl decreases, it does not decrease by a large amount. So x represents a very small number. So we can approximate 0.5 minus 2x as just 0.5. And so if we do that, the calculations are much more simple. We no longer have to solve a quadratic equation. And so solving this, we get that x is equal to 1 times 10 to the negative second. So using this x, we can calculate the equilibrium concentrations. And notice how for NaCl, if we do 0.5 minus 2x, if we round that number, it's just 0.5. So the concentration of NaCl hardly changed at all, which is what we expect since the K is so small. The reaction will be very reactant favored. And then the concentration of NO and Cl2 is 2x and x, which are these numbers. So there are very few products at equilibrium. And then the last thing we want to do is check that approximation was actually valid. So we do this by comparing the change that we ignored, 2x, with the initial value, 0.5. Because remember, we simplified 0.5 minus 2x. We ignored the 2x and just simplified it as 0.5. So plugging in x, this ratio of the change to the initial value is 0.04, which means the change that we ignored was only 4% of the initial value. So in general, if the term that you ignore, this 2x, is less than 5% of the initial value, which is 0.5 here, then your approximation is justified. So here it was 4%, so we were right in making this approximation.